we start with modeling of DC servo motor. So, the motor is a very important instrument, or we can say device, which is useful in control applications. Whenever a control engineer develop any algorithm, it has to verify in real time. So, the DC motor is a very important problem. Therefore, there is need to study the modeling of this motor. There are two types of motors, AC motor and DC motor. So, first of all we see what are the differences between AC motor and DC motor. Now, if you compare the DC motor and AC motor, which is the best? So, first of all we see what are the advantages and disadvantages of AC motor. Now, about the advantages: lower cost, higher efficiency, lower inertia, maintenance is less since there is no commutator and brushes. These are some advantages of AC motor, but there are some disadvantages, because finally what is the result? Result we require output. So, we will find that output which obtained by AC, it is difficult to control, and again the characteristics, particularly torque peak characteristics, is somewhat non-linear. Therefore, for analysis point of view, the AC motor is not better in comparison to DC motor. So, what are the disadvantages? AC motors are difficult to control for position control such as robotics applications. As I told you that last time, that we have to control the position of a robotic arm. So, how to control it? So, here suppose this is an arm and this arm is there and this is the point, gripper, and here the gripper is picking some object and it places it. So, what happen if you move like this? So, here it has to come this point. So, here we will find that the controlling task or moment is not so proper. So, that is the one disadvantage of this AC motor. Second, the characteristics are quite non-linear, therefore, analysis is quite difficult. Now, what are the applications? AC motor are useful for low power application because of the things that analysis is quite difficult. Therefore, if you go for higher order system, it is difficult to use this AC motor. So, in that case we will see later on the DC motor is quite better. Now, about the DC motor, the characteristics of DC motor are linear in comparison to AC motor, and these motors are easier to control. If you see the control aspects, these motors are very easy to control. Then there are some disadvantages. The DC motor are quite expensive due to involvement of brushes and commutators. See, in the DC motor there is involvement of brushes and commutator, and naturally the size increases, and again we have to maintain this brushes and commutator, and therefore it is quite expensive. But today, due to development of the power electronics engineering, a brushless motor has also come. So in other words we can say that now a DC motor are better in comparison to AC motors. Now, application, it is used for high power applications. So, as the controlling is quite easy, therefore we can use this motor for higher power applications. Now, about the servo system. Normally those who are studying electrical machine subject normally called as motors, AC motor, DC motor. But whenever this motor we have to use in control, it has to call as servo motor. What is servo? Servo means your output, it is in terms of position, velocity or accelerations. So, here point is servo means output is some mechanical variables like position, velocity or acceleration. Now, what is the requirement of such type of AC motor? What we want that the motor, once we give input, motor should immediately on, that is rapid acceleration from the standstill. So, that is the requirement of AC motor. So, it is written servo application, DC motor is required to produce rapid acceleration from standstill. The physical requirement in such type of motor are of low inertia and high starting torque. So, this is possible, rapid acceleration is possible whenever there is inertia should be less, then and then we get high starting torque. So, this can be possible by reducing the armature diameter. So, we have to reduce the armature diameter with consequent increase in armature length such that the desired power output can be achieved. So, desired output can be achieved by reducing the armature diameter, which consequently increase the armature length. So, you can see this reference. So, this DC motor can be used in two modes. One is called armature control mode and another is called field control mode. So, what is the difference between armature control and field control? In armature control mode, we have to keep field current constant, and in case of field control mode, we have to keep armature current constant. Now, we have to see the modeling of DC servo motor in both cases, that is in armature control mode and field control mode. So, we will see this part. Okay. Now, first of all, now we are developing the transfer function model of a DC servo armature control motor, and afterward we will develop the state space model of an armature controlled DC servo motor. So, first of all, I am drawing the circuit diagram of an armature controlled DC servo motor. So, in a armature controlled DC servo motor, or if you say any motor, there is a involvement of armature resistance, then we have inductor, and here is brushes. These are brushes, this one and this one. So, is armature resistance, this is inductors. Then we required a field winding. So, here we say armature winding, but here we need a field winding. Now, here is this field current, E is here applied voltage. Now, here we will get a back EMF, and here is the armature current. So, now when this motor will rotate, it has to drive against moment of inertia and the frictions. So, here is by J, B, and now the torque produced by the motor Tm. T is the torque produced by the motor, and here is the theta positions. Okay. Now, this is a circuit diagram of an armature control DC servo motor. Now, here main requirement is the position theta. Now, this is motor. Now, first of all, we see what is the difference between the generator and motor. In generator, we will get the EMF. So, how we are getting the EMF? When the conductor cuts the flux, the EMF is induced. The flux, how the flux is produced? By the field winding. And in case of motor, when the current carrying armature winding cuts the flux, then EMF is induced. So, that is the basic difference between the generator and motor. In generator, we get the output voltage. In case of motor, we get the torque. So, in case of motor, when current carrying conductor cuts the flux, torque is produced. Generator, conductor cuts the flux only. In that original conductor, there is no current is flowing. That is difference between generator and motor. Therefore, if you see in this particular diagram, circuit diagram, we have applied voltage. So, applied voltage to this motor means that it is to the system, that is why it is called as the motor. So, here we will find that this is a field winding. So, what is the purpose of the field winding? Is to produce the flux, and this is the supply to produce the field current. So, as IF changes, the field current changes, or IF changes, the flux changes, and this flux is responsible for this getting the torque. then when this conductor here cuts the flux, we get the torque. And now here is the EB, a back EMF, and he is the applied voltage. And now our main purpose is to develop a transfer function model of this servo motor. That is, our main purpose is to get theta s by E of s. Now we start deriving this. Now what is the first step? The first step, we see that this field current, because of this field current, the flux is produced. And if you consider linear range of magnetization curve, so we write the expression as the flux is proportional to your field current. Flux is proportional to your field current, and here we assume linear range of magnetization curve. Therefore, you write this expression as phi equal to K1 equal to, this is be replaced by K1. Now finally, what is the aim of the motor? Aim of the motor is to produce a torque. The torque is proportional to flux and armature current. Therefore, the torque developed by this motor is proportional to where flux into armature current. Now this is a proportional sign, we can also remove it. So we can write motor torque equal to K1 flux into armature current. So now here this is flux, this flux we already determined. So what we can do, we can replace this flux, equation of flux here. So we will get K1, this actually we take this Kf, this is K1, Kf If into I. So this flux is proportional to Kf into If, the motor torque is proportional to flux into armature current. So this flux we are replaced by Kf into If here, Kf into If, and this is an armature current. So in this case what we are doing, we are keeping the field current constant, this current we have to keep constant. Therefore, what we can do, this K1 is also constant, this K1 constant, this Kf is a constant of this, and this If we have to keep constant. Therefore, this total K1, Kf, If we replace by another constant. So Tm motor torque equal to Kt into I. Let us say this is equation number 1. So we have got the motor torque. Then about the back EMF. Back EMF is very important in motor, because whatever the current flowing in the motor depends upon this back EMF. Because if you see the back EMF EB equal to phi Z N 60 P by A. So this expression you might have studied in electrical machine subject, that is flux, number of armature conductors, speed, P poles, A is the number of parallel path, and here this EB is proportional to speed. So this part you have studied in electrical machines. And what is the important role of EB? Important role of EB is in the initial current. If you see the motor, the initial current I equal to E minus EB, we can take small EB here, EB divided by RA. So if you start the motor, what happens? When you start the motor, speed is very less. So when the speed is less, what is the EB? Because EB is proportional to speed, therefore this EB is also less, and that's the current is E by RA. Current is in this case E by RA, and this is quite large. But as start the motor, as motor gathers speed, EB increases, the armature current decreases. So this EB in this case is just like a starter, it controls the armature current. So now here we have to write down the expression for this EB. This EB is proportional to d theta by dt. because theta is position, d theta by dt is the speed. Therefore, we removed here a proportionality sign, we will get Eb equal to Kb d theta by dt. This is equation number 2. So, we have got equation number 1 for motor torque, we have got expression for back EMF. Now, what are the things which are involved in this motor, that is resistor, inductor. So, this part we have not covered. So, that part also we have to taken into the expression of the modeling. Therefore, what we do, we apply a conventional Kirchhoff's law to this part. So, what expression we will get? E applied voltage equal to LA dIA by dt plus RA into IA plus EB. This is equation number 3. This is nothing but your RA into I, that is armature resistance into the armature current, LA di by dt plus EB. EB is the back EMF. Now this part is completed. Now coming to this part. So J, moment of inertia, and B is friction. As we apply the torque is coming in the existence, electrical torque, but it has some motions. Just like if I am walking here, so I am applying my force. So it is opposed by my inertia, my body weight. Similarly, when motor starts rotating, it has been opposed by the moment of inertia J and also the friction. The friction is with viscous friction. Last time we have seen this. So here, therefore, here also we can write the expression of the torque developed by the motor. That is a mechanical torque. So here we can write the expression like this: torque equations J d square theta by dt square plus B d theta by dt equal to TMT, and this OD we have derived, that is equal to KT into I. Now this is equation number 4. So these are equation 1, 2, 3, 4, and all these equations covered the model of this servo motor. Now, but our main purpose is to get the model in terms of S, that is theta S. Theta is the position, theta S by ES. E of S is the applied voltage. Now, what is the next step? So it means that we have to apply the Laplace transform to all these equations 1, 2, 3, 4, and doing some mathematical adjustment, we have to get theta S by ES. So whatever thing now I am explain, now again you see it in various steps. So first step, that is torque equations. The flux is developed due to the field current. This flux is proportional to field current, assuming linear range of magnetization curve. So flux is proportional to IF, so flux equals to Kf into IF. So we have seen this expression earlier. So this is next. This torque is proportional to product of armature current and air gap flux. Therefore, this motor torque equal to armature current into flux. So this is expression. Then replacing equation 1, this equation 1 in equation 2, this 2. So we got TMT, and here this part is replaced by a constant KT. Therefore, motor torque equal to KT into I. Then equation of armature circuit, differential equation of the armature circuit is determined using Kirchhoff's law, which is given below. So E RAI LA dIA by dt plus EB. Then third, we know that back EMF is proportional to speed. So EB equal to KB d theta by dt. Then replacing equation 5, this 5 in equation 4, this 4. So we will get expression as E RAI LA dI by dt plus KB into d theta by dt. Step 3, torque, mechanical effect. The electrical torque rotates the load at speed theta dot against the moment of inertia J, and the viscous friction coefficient B, so this is given as like this, J d square theta by dt square, B d theta by dt, TMT kt into I. So this is the expression. So whatever we have explained earlier, all these, so this is represented here, all these equations. Now we have to develop the model in transfer function form. So definitely we have time domain, so we have to apply Laplace transform. So here this all this equation I have written again, so that we can easily write down the expression in S domain. So here E, so we write Laplace of E, E of S, RA into I of S, the LA this, ESIS, and this EB equals EB of S. Then about this equation number 6, this EB is represented by EB of S and this constant KB, and this d theta by dt, the theta dot, is represented by S theta of S. Then motor torque J d square theta dt square, B d theta by dt, motor torque is kt into I. So here J is d square theta dt square, that is it is theta, you can say dot double dot, that is represented by S square theta S. Then d theta by dt theta dot is represented by S theta S, and this TMT of S, and here this is kt into I of S. Now 8, 9 and 10, these equations we got. So what we were doing here, you see equation number 8, from this equation 8 we are taking I of S outside, so we have got this, and again we have determined EB of S, this is EB of S, this is equation number 8, and now here equation 9 corresponding to this EB of S, and now what we do, replacing EB of S here, so we got I of S like this, and again replacing the equation of I of A of S in equation number 10 this, so you will get these equations. So we will J square theta S plus BS theta S TMT KT into ES, this part is basically your IA of S, this I of S, and now we are solving, cross multiplying, taking some elements common, and finally we have reached the expression for GS equal to theta S by ES equal to KT JS plus B RA SLA KT into KB. So this is a transfer function model of a DC servo motor which is in armature control mode, and again we will find that it has one pole at origin. This is a type 1 system, and here open loop plant here for the position control is not stable. This is the one important point we can observe. So all the stability issues regarding this we will see later on, but just know that this modeling issues has come, so this is very important point to be noted. Sometimes instead of position we require a speed control. So in that case how will you get the model? So we have got the model like this, this is the third order model, here S, but if you go for the speed control, can we get the same third order model or can we get the fourth order model? Now this need to be verified. Therefore now we are doing here the model of a DC servo motor armature control, that is basically speed control model, speed model. So theta of S is position, so S theta of is velocity, so time domain theta t, S domain theta of S, then time domain get theta d, S domain equals to S theta of S. This is for the position and this is for velocity. So GS position equal to theta S by S equal to KT S JS plus B RA SLA KT KB, that is same expression, this expression. And when we are moving to the speed, so what will happen to the speed here, S theta S by S, that means your S is cancelled and you will find that the model of a DC servo motor, that is a speed control model, is second order, whereas the position is third order, and we will find that this model, this is second order system, and you know that when all the coefficients are positive, the system is always stable. So all these are positive, if positive, this model is a stable model, that is open loop stable, whereas this open loop a stable model. And this is third order, that is armature control model is particularly position control model is third order, whereas speed control model is second order model. Now you just see the block diagram of a position controlled DC servo motor. You will find that this is 1 by LAS by RA. That means you see the original figure, as we apply input it has to move towards RA and LA, and because of this RA and LA the current is flowing, and this current flowing, and because of the current flowing a torque is produced, and torque is opposed by this J and B. Therefore, first of all we have written the expression for LASRA, then this is constant rotor constant. We have got a torque, and that torque is opposed by 1 by Js plus B, and this is the back EMF. And if you want a speed, a position, we got theta s 1 by s. So this EAFS input opposed by back EMF, and because of that current is flowing which drive through this LAS by RA, then is a motor torque constant. So that means the motor torque is produced, and that has to drive the motor against 1 by Js plus B. This is the velocity, and this is, we can say, a positions. The block diagram of a velocity controlled DC servo motor, same thing, but we are done here. Here theta dot s, same 1 by LS RA, KT, Js plus B, and this is KB. Now the simplified form of transfer function model. As I have seen that the model, that is a position control model, is third order. In control literature we will see that there are various model organization techniques are available. They can reduce the model higher order to lower order model. So there are some techniques are available, but can we do that from the model itself, just looking after it, can it reduce to second order or first order without using any techniques? So just see the model here. In this model we have G position is S Js plus B RA SLA KT KB, but you know, if you take the armature inductance of armature is very small, so that we can neglect it. So here we have neglected this LA. So what we have written here, inductance LA is usually small, therefore it can be neglected. So here after neglecting LA, and you will find we get this expression. Again we have some modified this one, and finally the position control model we have got like this, and here this B KT by K is replaced by another constant. So here G position S equal to KT by RA, J square S B KT KB RA, that is equal to KT RA J square B0 S, where B0 equal to B KT KB RA, that means this B0 is like this. So B is the friction which opposes the motion. So what will happen? Here KT KB, they are responsible for the back EMF. So what happened? Because of this back EMF, the viscous friction is also increases. So above equation indicates that the back EMF of the motor increases viscous friction of the motor. So in above equation B0 increases the viscous friction of the system, and again it has been simplified, and we have got the Km equals to KT B0 by RA motor gain constant, and tau m J B0 motor time constant. So that is the simplified model of an armature control DC servo motor, particularly this is your position control model. And if you want a speed control model, so we can write down as Km tau m S plus 1. So this is model is a speed control, and this speed control model it reduced to first order. So see here, this is a motor, and this particular motor model we are used to only first order particular speed, whereas in case of position control it become a second order model. And therefore suppose in motor what is the requirement? Requirement is for speed. Suppose we want a speed of 1500 rpm, and suppose we are not getting exact speed. So what we are doing? We design a controller. So at that time this model which you have determined now, this is helpful in the designing of the controller. Now this is the model which is concerned with the transfer function, but now we are running the advanced control. For the advanced control, we are using the state space modeling. So in the state space model, we have seen that based on the system we have to assume the state variable. So here now the state space representation of an armature controlled DC servo motor, that is same system which we had determined earlier. So we have to determine its space model. So what we have done, theta s by s equal to km s term ms plus 1. So now we have done cross multiplication. So this is cross multiplication. After that, after solving this, we have got tau m theta dot t plus theta dot t equal to km into e of t. In above equation, we write output as a first state variable and other variable as the derivative of the output variable. So here we have taken x1 of t equal to theta of t, x2 of t equal to theta dot t, then x2 dot of t equals to theta double dot t. So because why? Because here we require theta dot t, therefore x1 of t equal to x2 of t, and therefore after solving this, that is this equation, these particular equations, we come across the value of x2 dot t is like this. And finally this model has been presented in a companion form or controllable canonic form. So we have got this particular results. That means we have started with the transfer function model, that is a classical approach, and from classical approach we have developed an state space model. Now, this is a one type of approach, but in sometimes we can design a model or we can develop the model based on the variable which is involved in our system. As we have seen last earlier classes, that we have to consider the variable as the energy storage element or very important variables. So here we will now develop the model of a DC servo motor in a state space considering the variables, and we will see is there any difference. So first of all we will consider state variables. So in this case, let us say step 1, selection of state variables. The state variable selected as position, speed and the armature current. So there are 3 state variables, because we have got expression in terms of d theta by dt, d square theta by dt square, and armature current is also very important here. Therefore we have considered these 3 state variables, and we have already determined the equation for armature circuit, back EMF and the torque equation of a motor with reference to the moment of inertia and the friction. So these are 3 equations, and now these variables we have to adjust it in these equations. Now derivation of state space equation. So we write x1 dot equal to x2 d theta by dt, then x2 dot equal to d square theta by dt square. Now this expression j d square theta by dt square, b d theta by dt equal to tmt, t means motor torque constant, that is equals to kt into I. So here d square theta by dt square replaced by x2 dot, see here this, then d theta by dt, this is d theta by dt equal to x2, we replace by x2, and here kt into I into x3. And now after solving these equations we have got this x2 dot equal to minus b by j x2 plus kt by j into x3. Now this is an equation for an armature circuit. So E Ra into I La di by dt plus kb d theta by dt. And now again we have taken this part here and other part of right side we have got this, and again replacing all the state variables we have got expression for x3 dot like this. Now the state space model of an armature controlled DC servo motor can be written like this. So same x1 dot x2 dot x3 dot, that means whatever we have determined here, x1 dot x2 dot x3 dot, that is x1 dot x2 dot x3 dot, we have written like this, and from this x1 dot equal to x2. So here 0 1 0, or the input is 0, then x2 dot equals to minus b by j x2 here, x1 term is 0 here, so therefore it is 0, and here kt by j x, then x3 dot, this x3 dot equal to, so is there term of x1, just see here, see x3 x2, again here term of x1 is 0, therefore we are replaced by 0, and here term of x2 we have written as minus kb by la, and this term of x3 we are replaced by ra by la, and here particularly 1 by la is replaced by like this. Suppose the output is motor angle, therefore it can be written as y equal to theta, theta is x1, and this is expression. Now here we want output should be this is like a speed, just like position we have taken, now it is speed. Now we have variables we have to change. So here now my variable is x1 equal to omega equal to d theta by dt. That is the first variable d. There is no need for position variable here because we require speed. If we want position, we may have taken x1 equals theta, which we have seen last time, but here our purpose is to speed. Therefore what we have done, we have taken d theta by dt equal to x1, and second variable, because we have to control armature also, armature current, therefore x2 equal to I, and therefore we write in the expression Ga d theta dt square b d theta by dt motor torque k2 into I, and now here d theta by dt equal to omega. So it has been replaced like this, J d omega by dt b into omega k2 I into x2, and here j x1 dot b x1 k2 into x2, and now this equation is solved. Then equation of an armature circuit E Ra, what is I into x2, La di by dt x2 dot, and kb into d theta by dt equal to omega. So we have written omega, and again we have solved it, we have got this equation, and from this we have got this, the x2 dot equal to minus kb by la x1 minus ra by la x2 plus e by la. So this is the expression. So state space model is given as like this. Just see here we have got two state space model. One state space model we have determined from the transfer function approach, and one state space model we have determined by this actual approach, that is actual state space approach. Then can we get the same result, or can we get the same roots of the matrix, that is matrix A, this is matrix A, and earlier also we have determined this is matrix. So this is matrix A we have determined. So can we get the same eigenvalue or same performance? So this is a very important issue. So in future when we learn the stability and performance, we will again come with this modeling part, or again we take this model and we check the performance. But here for modeling point of view we have got models. So that means the state space model we can determine from the given transfer function, or we can determine from the state space models. Now these are some references. Thank you.